Carefully formulate the negations of each of the statements in 5 through 7, then prove each statement by contradiction. So the statement that we need to prove is that there is no greatest even integer. That's true, but instead of proving that this statement is true, what we're going to do is we're going to show that the negation of this statement is false, which is essentially the same thing logically, but the strategy looks different. So instead of proving that there is no greatest even integer, we're going to first negate this statement. Since the original statement says there is no greatest even integer, then the negation would say that there is a greatest even integer. So now that we have the negation, we can see what our proof is going to look like. We're going to assume that the negation is true. Assume there is a greatest even integer. And with this, we're going to try to deduce a contradiction. If this statement is true, then the negation is definitely false. This statement is false. And so you might ask yourself, why would we assume something that's false? Well, when we assume a false statement is true, then math gets weird and eventually we deduce a contradiction. And by deducing a contradiction, we have to call into question this one assumption, which leads us to prove the truth of the original statement. So if we assume that there is a greatest even integer, let's call it x. Now the question is, how are we going to create a contradiction? Well, the way we're going to do this is we're going to somehow undermine our assumption. We're assuming there is a greatest even integer x. Can we find a greater even integer that's greater than even the greatest even integer? I know that sounds weird, but that's the goal of this proof. Before we get into the contradiction, let's unpack a few definitions. Since x is even, then x equals 2k for some integer k. Now let's consider a special number x plus 2. Now since integers are closed under addition, then that means x plus 2 is an integer. Since 0 is less than 2, we can add x to both sides to show that x is less than x plus 2. So now we have an integer, x plus 2, that we've shown is larger than x, which we're assuming is the greatest even integer. And since we added 2 to an even integer, we should still have an even integer. So next I'm going to substantiate the claim that x plus 2 is even. By substitution, x plus 2 is 2k plus 2, which is 2 times k plus 1. And so x plus 2 is an even integer that is greater than the greatest even integer. That's a contradiction. So the contradiction is now in your face in the sense that we've brought about the contradictoriness of assuming a falsehood. This contradiction here undermines our original assumption that there is a greatest even integer. So that means we have to conclude that this assumption was in fact false, which means that there is no greatest even integer. So therefore, there is no greatest even integer. And that's because if there was, then we would be able to arrive towards a contradiction in mathematics. And mathematics is supposed to be logically consistent. So whenever we reach a contradiction, that's a big problem, and we have to call into question whatever assumptions that we made. Thanks, everyone, and I'll see you in the next video.